Welcome to Mech Cosmos, Engineering, Explained. Somewhere in the ocean right now, a city is moving. It has its own power plant, its own hospital, its own fire department, its own airport. It carries over 5,000 people, it weighs 100,000 tons, and it moves through the water at over 55 kilometers per hour. It is the most powerful conventional weapons platform ever built, and it projects the military power of a nation across every ocean on Earth without asking permission from anyone. The aircraft carrier is the most complex warship ever constructed. It is not just a ship, it is a complete military base that happens to float. A self-contained ecosystem of aviation fuel weapons, aircraft maintenance facilities, and the people needed to operate them all simultaneously in the middle of the ocean. Today, we explain everything. How the nuclear reactor powers it, how aircraft launch from a deck that is far too short for normal operations, how the electromagnetic catapult system works, how the arresting wire stops a 30-ton aircraft traveling at 270 kilometers per hour in under 100 meters, how 5,000 people live and work on this machine for months at a time, and how all of this comes together in a machine that has defined naval warfare for nearly a century. We are Mech Cosmos. Engineering. Explained. Let us begin. The modern aircraft carrier is best represented by the Gerald R. Ford class, the most advanced warship ever built. The Gerald R. Ford is 337 meters long. That is longer than 3 football fields placed end to end. Its flight deck covers 18,000 square meters. It displaces 1,000 tons of water when fully loaded, making it one of the heaviest moving objects ever created by human beings. It is powered by 2 nuclear reactors. It carries up to 90 aircraft, and it costs approximately $13 billion to build, making it the most expensive warship in history. But before we understand how the carrier operates, we need to understand why it exists. The fundamental value of the aircraft carrier is power projection. A land-based air force can only operate from airfields within range of the target. To use land-based aircraft against a distant threat, a nation must either have its own bases nearby or negotiate access to another nation's bases. This takes time, requires diplomatic agreements, and may not always be possible. An aircraft carrier eliminates this dependency entirely. It is a sovereign piece of territory that moves. It can position itself within striking range of any coastline on Earth within days. It needs no permission. It negotiates with no one. The carrier strike group can conduct sustained combat air operations, delivering hundreds of strike sorties per day against targets hundreds of kilometers inland. No land-based air force can be deployed with this speed, this flexibility, and this independence from host nation support. This is why the United States has maintained a fleet of 10 to 12 carriers continuously for decades, and why every other major naval power has sought to develop carrier capability of their own. When a crisis emerges anywhere in the world, the first question asked by military planners is, where are the carriers? The answer determines what military options are immediately available. The nuclear propulsion system is the foundation of the carrier's extraordinary capability. 2 A-1B nuclear reactors generate heat through the controlled fission of enriched uranium fuel. This heat produces steam that drives 4 massive steam turbines. Each turbine is connected through a reduction gearbox to one of 4 propeller shafts. Each shaft drives a 5-bladed propeller over 6 meters in diameter. The combined output of the 4 shafts exceeds 26,000 shaft horsepower, enough to drive this 100,000-ton ship through the water at over 55 kilometers per hour. The nuclear fuel lasts for the entire 50-year service life of the ship without any refueling. This gives the carrier essentially unlimited range. It can steam continuously for decades. The only constraints on its endurance are food for the crew and aviation fuel, and weapons for the aircraft. Both can be replenished at sea from supply ships without the carrier ever returning to port. The 2 reactors on the Gerald R. Ford produce approximately 700 megawatts of thermal power. This is not just used for propulsion. The carrier requires enormous amounts of electrical power for its weapons systems, radar arrays, communications equipment, the EAL's Catapult System, and the daily needs of over 5,000 people, The nuclear reactors provide all of this power with enormous reserve capacity. A conventional oil-powered carrier would need to carry and consume enormous quantities of fuel simply to generate this electrical power. Fuel that would have to be replenished regularly, limiting the ship's endurance and operational flexibility. The flight deck is the most complex and most dangerous workplace on Earth. During intensive flight operations, an aircraft either launches or recovers approximately every 90 seconds. Up to 2,500 individual aircraft movements can occur in a single day. The deck is constantly populated with hundreds of personnel, all operating in an environment of extreme noise, jet blast heat, and the continuous movement of aircraft weighing tens of tons. Coordination of all these people and machines requires a precise and well-understood system of roles and visual identification. Every person working on the flight deck wears a colored jersey that immediately identifies their role to everyone around them. Yellow jerseys are aircraft directors. They physically guide every aircraft movement on the deck using hand signals. Green jerseys cover a range of roles including catapult and arresting gear crews and maintenance personnel. Red jerseys handle weapons ordnance and crash and salvage operations. Purple jerseys, known as grapes, handle all aviation fuel. White jerseys include safety observers, quality control personnel, and medical staff. Brown jerseys are plane captains responsible for specific aircraft. This color coding system allows the air boss observing from the island to instantly understand what is happening anywhere on the deck and allows every worker to immediately identify who they are working alongside. Launching an aircraft from a carrier is one of the greatest engineering challenges in the entire system. The flight deck is approximately 330 meters long. A modern strike fighter like the F-18 Super Hornet needs approximately 450 meters of runway to take off at its maximum takeoff weight under its own power. The carrier deck is simply not long enough. The solution is the Catapult, and the Gerald R. Ford class uses the most advanced catapult system ever built. The electromagnetic aircraft launch system, ELS, replaces the steam catapults used on all previous American carriers. Steam catapults worked by storing enormous quantities of high-pressure steam and then releasing it in a controlled burst to drive a piston along a track. ELS uses an entirely different principle. It uses a linear induction motor, a conventional electric motor unrolled into a straight line, to accelerate a launch carriage along a track set flush into the flight deck. The aircraft's nose landing gear is attached to this carriage through a launch bar. When the catapult fires, an enormous surge of electrical energy stored in large, rotating kinetic energy storage devices called energy storage rings is released into the linear motor. The electromagnetic force accelerates the carriage and the aircraft attached to it from 0 to over 270 kilometers per hour in approximately 2 seconds along a track just over 100 meters long. The aircraft leaves the end of the deck at flying speed and climbs away. ELS delivers several critical advantages over steam catapults. The energy delivered can be precisely programmed for each individual aircraft launch based on the aircraft's exact weight and configuration. A heavy, fully armed strike aircraft needs maximum energy. A lighter aircraft needs less. Steam catapults delivered a fixed energy output that had to be set conservatively to avoid overstressing lighter aircraft, meaning heavier aircraft were sometimes under-energized. EALs eliminates this limitation entirely. It also has fewer moving parts than a steam catapult, requires less maintenance, and takes up significantly less volume below the flight deck. Recovering aircraft, landing them back on the carrier, is even more demanding than launching them. Landing on a carrier is consistently rated by military pilots as the most difficult and most demanding flying task in existence. The pilot must fly a precise approach to a deck that is moving in 3 dimensions, pitching, rolling, and heaving in the sea, at night or in bad weather, and touch down in a landing zone only about 10 meters wide and 30 meters long. The approach must be flown at exactly the right speed and exactly the right angle. There is almost no margin for error. The optical landing system, a series of lights mounted on the port side of the flight deck, provides the pilot with precise glide slope information during the approach. The system projects a central amber light called the meatball surrounded by green datum lights. If the pilot sees the meatball above the datum lights, they are too high. Below the datum, they are too low. Centered on the datum, they are on the correct glide slope. The pilot calls the ball over the radio when they acquire the meatball, confirming they have visual glide slope reference. From that point, the pilot focuses entirely on keeping the ball centered while simultaneously maintaining speed heading in lineup with the landing area. The aircraft touches down at approximately 250 kilometers per hour. Its tail hook, a hook mounted on the rear of the aircraft, must catch one of 4 steel arresting wires stretched across the landing area at intervals of approximately 12 meters. The ideal wire to catch is the third wire. Catching the first wire means the approach was slightly low, and catching the fourth means slightly high. Each wire is connected through a system of pulleys to arresting gear engines located below the deck. When the hook catches a wire, the arresting gear engine applies a precisely controlled hydraulic braking force that brings the aircraft from 250 kilometers per hour to a complete stop in approximately 100 meters in about 1.5 seconds. The deceleration force on the pilot is approximately 4G, 4 times the force of gravity pressing them forward into their harness. If the hook misses all 4 wires, the pilot must immediately apply full engine power and fly off the end of the deck for another approach. This is called a bolter. The island superstructure on the starboard side of the flight deck is the operational nerve center of the entire ship. It contains the navigating bridge where the officer of the deck conns the ship. It contains the flag bridge from which the admiral commands the entire carrier strike group. At the very top is primary flight control, universally known as Pri-Fly. This is the domain of the air boss, the officer with absolute authority over every aircraft within 5 nautical miles of the carrier and every movement on the flight deck. The air boss watches the entire operation from the Pri-Fly windows and coordinates launches, recoveries, and deck movements in a continuous flow of radio calls and decisions. Nothing moves on or near the carrier without the air boss's knowledge and approval. Below the flight deck, the carrier contains an enormous internal volume organized across multiple levels. The hangar deck immediately below the flight deck provides covered maintenance and repair space for aircraft. It is connected to the flight deck by 4 large deck-edge elevators, hydraulic platforms that can lift a fully loaded combat aircraft from the hangar to the flight deck in seconds. The weapons magazines deep in the ship store the enormous inventories of bombs, missiles, rockets, and ammunition required for sustained combat operations. Aviation fuel tanks hold millions of liters of jet fuel that must be pumped to the flight deck continuously during operations. The food service facilities prepare 3 full meals per day for over 5,000 people. The medical department includes operating rooms, intensive care units, dental facilities, and pharmaceutical services, capable of handling any medical situation without evacuation. The carrier operates as the centerpiece of a carrier strike group. Typically, the group includes 1 carrier, 1 guided missile cruiser, 2 or 3 guided missile destroyers, 1 or 2 attack submarines, and a combat logistics ship. The cruiser and destroyers provide layered air defense against aircraft and missiles that might threaten the carrier. The submarines provide undersea protection and conduct intelligence gathering operations ahead of the group. The logistics ship replenishes fuel, food, and ammunition at sea through underway replenishment, a complex procedure where ships steam in close formation while fuel lines and cargo transfers connect them. This capability allows the strike group to remain at sea indefinitely. The aircraft carrier represents one of the most ambitious and successful engineering undertakings in human history. It combines nuclear propulsion, electromagnetic launch systems, precision landing systems, advanced weapons handling, and the life support infrastructure for a small city into a single mobile platform that can be deployed anywhere on Earth within days. It has been the decisive instrument of American military power for 8 decades, and it remains today the most powerful conventional military platform ever created. That is how an aircraft carrier works. We are Mech Cosmos. Engineering explained. If this video gave you a new appreciation for the most powerful warship ever built, then subscribe, hit the notification bell, and join us for the next video, because every machine has a story, and we are here to tell it.